This question states, if a thin-walled spherical pressure vessel with radius r and wall thickness t has internal pressure P, what is the sigma coordinate for the location of the center of the Mohr circle? And follow-up question, what is the maximum in-plane shear stress? Well, let's go ahead and start calculating out some values and making some drawings of a Mohr circle based on the state of stress that we're given for a thin-walled spherical pressure vessel. So this element could be at essentially any angle relative to a radial vector coming out of the center of a sphere. And sigma 2, you might see this in Hibbeler's book or in other places. Why not sigma 1, sigma 1? Well, sigma 1 is often reserved for the hoop stress in a cylindrical thin-walled pressure vessel, and we know that's PR over T. And sigma 2 is sometimes reserved for um, axial stress in any direction on the surface of a spherical pressure vessel, because that's PR over 2T, so that's smaller. So it can be a little bit confusing because you're like, wait, sigma 1 is supposed to be the larger principal stress, but there's not a sigma 1 here. There's just a sigma 2. And actually, the meaning of that might become a little bit more clear in just a second. But you could have written sigma 1 if you had wanted. Sigma 1, but either way is fine. So we have an x direction and a y direction, and we'll say sigma 2 is equal to PR over 2t. And now, to draw a Mohr circle, we will calculate the average sigma, the sigma average, right? Which is what you would have sigma x plus sigma y all divided by 2. So that's just going to be sigma 2 plus sigma 2 divided by 2, that's equal to sigma 2. So the center of Mohr's circle will be sigma average comma 0 on the sigma tau axis, as you see here. And so here is the center of Mohr's circle. Now, what do we do next? Well, you typically would pick a point on Mohr's circle and go ahead and plot it, and then calculate the radius. Okay, well, what's a point on Mohr's circle here? Well, it could be sigma x comma tau xy or sigma y comma minus tau xy. Those are two valid points. What is tau xy? What is sigma x? Well, sigma x is just sigma 2. And tau xy is equal to 0. Okay, so tau xy is equal to 0. Sigma 2 is actually sigma average. So if I draw a point on Mohr's circle, it is just, again, on that dot. And sigma x is equal to sigma y. So if I go on the other side, sigma y is going to be, or sigma y prime, right? That would be equal to the sigma 2 comma tau xy. This is fun, maybe not funny, but interestingly fun, I think, because Mohr's circle in this case is just a dot. Now, what does that mean if the whole circle is just a dot? Any rotation I do at that location, of the Mohr circle, is just still on that dot. And at that dot, the radius is 0, right? Because the tau xy continues to be 0 for any rotation. If the radius is 0, that means we're never going off of the sigma axis in the vertical direction. And so that means that the tau is always going to be 0, which means that the maximum in-plane shear stress is just equal to 0. So this is one of those classic examples where we gain some insight by using Mohr's circle. But if we had also looked at the problem itself and said, hey, you know, a sphere is radially, polarly, if that's a word, azimuthally, azimuthal, I can't even say that word, but you know, it's symmetric. It's a sphere, it's a ball, right? And so if we take any element on that sphere, we already kind of know the state of stress is going to be sigma 2, sigma 2 for, two orthogonal axes. And we rotate this any amount, and Mohr's circle confirms what we might have already known. There's never going to be any shear stress, at least in that plane. More on that soon. Thank you. I hope you find this video helpful.